Hi everyone. So in this video, we are going to talk about how to create a heap using an array in place. So remember in the last video, we said that, well, heaps are not, even though we draw it like a tree, we actually implement them with an array. So if we are implementing them in an array, how do we create them if we were to be given an array of values to begin with? So if we have an array of numbers and we just want to turn it into a heap, what's the algorithm to do this? So the way you do it is actually by simply, there's actually an algorithm to build an array, build a heap out of an array without actually creating a heap object. So the slow way is obviously, oh, I'm going to write this heap class. There's going to be an insert function and a remove function, and I'm just going to insert everything into the heap, right? Don't do that. The faster way is actually to simply take the array and build the heap right in the array itself, and it's actually a very nifty little algorithm. So let's talk about that. But before we do that, let's talk about an algorithm called heapify. So when we have a heap, okay, so here's our heap. Ignore the fact that the top is empty. We're going to do something with that in a moment. What we're going to do, what I want you to note about this heap is that if I look at just the left subtree of this data structure right here, this itself is a heap. If I look at the right subtree, this thing is also a heap. So the two sides are both heaps to begin with. Now, if we take any number, and let's say that the root was somehow emptied, like it was during erase, if we put any value into this data structure, we can actually very quickly place this value. This is effectively what we were doing with remove. What we did was we said, okay, if we take this number, we compare this value against its left and right child. So instead of keeping the node empty until we find where it should go, put the number in, compare that number against its two children. And if we do that, if the number is already in place and we compare it against its two children, we say, okay, compared to the smaller child, the left and right children, who has the highest priority? So in this scenario, 3 has a higher priority than 6, right? So what do? We swap 3 and 11 because obviously 11 has a lower priority than both 3 and 6. And compared to 3 to 6, 11 is also lower priority than 3. So we swap 11 and 3. Okay, again, it's a downward movement. It's never left and right. So 3 doesn't go and become the left the left child or anything like that. We just simply take the 11 and we say, okay, let's compare it against its left child. Okay, definitely we're going to be doing at least a swap. So what we do is we determine whether or not we're going to swap it with the left child, or if the right child is smaller than the left child, then we swap it with the right child instead. And that's what happened here. So take the 11, put it in. Oops. Now, compare 11 against 15. Is it okay? 11 against 15 is perfectly fine. So all we have to do is compare 11 against 4. And if 11 and 4, in this case, it's no good because 4 is higher priority than 11. We're going to take this value, oops, this one here, and we're going to do a swap. So take the 11 and swap it with the 14. Okay, having a hard time swapping here. So let's just move it. So take the 2, swap them up, and then we're basically done. This is the heap as it should be after we do something called heapify. So this is the heapify algorithm. Given two children subtrees who are both heap, we can take the root node and effectively put any value in it and figure out how to form a heap with this extra node at the root. Okay, but the precondition is the two children themselves must begin as heaps. Okay, if children are heaps. Okay, so you can add a root node between two heaps if the children themselves are heaps. That's sort of the rule, okay? So you can't do this unless the left child and the right child are both heaps to begin with. Um, so it's basically what we do in remove. We just simply do the swapping without actually, instead of like thinking of it as an empty spot that we move down. But it's basically the same algorithm. So how does this work in terms of why do I want to know this? Like, why do I want to do this? Well, it turns out that if you have an array of values, you can turn it into a heap by effectively reapplying this function over and over again. So here I have an array. Now, clearly this array is not a heap. It's not a max heap. It's not a min heap. I know 8's at the root, but if you look over here, this is not a max heap. So it's not a heap. How can I build a heap from here? Okay. So, so what we do is we're going to make a heap, make heap by applying heapify over and over and over and over. Okay, so that's basically how you do it. You take the idea that we just talked about, the heapify function, and you apply it to the tree, starting at the first node that may not already be part of a heap. So what does that mean? Well, remember our tree is created with the nodes going left to right. Okay, so if I think about it, any node that is a leaf node is definitely a heap by itself, right? So if I take a look at each node by itself, I look at just this subtree right here, okay, where the 7 is. This subtree, that is a heap, okay? It's a heap with one node, but it is a heap by itself if I look at it just as that one tree. Similarly, this one over here, this is also a heap already for sure. I don't have to even look at the values. Those are heaps. So any leaf node is a heap. Okay, any leaf node is a heap. Okay, so we don't have to consider any node that is a leaf. Now, why is that actually important? Look at how many leaf nodes there are in this tree. There are 4 leaf nodes and 4 nodes that are non-leaf nodes. That's a lot. So in other words, at most, we're looking at maybe half the array. That's nice, okay? So if I were to add one more node, there's now 5 leaf nodes and 4 non-leaf nodes. So I only really have to look at half the array when I do this. I don't have to look at the whole array. I don't have to look at every single value because anything that's leaf is already in a heap by itself, right? Anything that is not in a heap, um, anything that's not a leaf might not be correctly heapified. So we have to actually apply heapify to it. Okay. So if I added an extra node here, okay, that actually means that I still start at the same place because this is actually the first node. If I look at it from the bottom going left, that's actually the first node that is not that I don't know if it's going to like break the heap rules, right? But any leaf node that I look at, I don't have to look at them. So I start basically in the middle of the array. Okay, there's in the notes there's some math formula that kind of works out like this is the node you have to start at, but effectively you start in the middle of the array for this. So we don't have to look at everything. At most, we look at halfway through. Okay. Now, what do we do with this node? Well, basically, we start by saying, okay, let's pretend that this is my heap, and I had just took 4 and put it into the root, and I want to know that this is a heap or not, right? So I compare it against its children, there's only 7, and say, is this still a heap? And if the answer is yes, you're done. If the answer is no, you have to do the heapify, which might actually break a heap further down, and then you have to apply heapify again. But right now, if I look at this thing on its own, just the 4 and the 7, that's perfectly fine. I don't have to touch this at all. So I don't. I'm just going to leave it alone. Okay. Now I go backwards. And going backwards, basically, remember, I just have to do this in my array. So like the algorithm, it looks complicated on the heap side, but effectively, all I'm doing is I'm like working backwards from the middle, going towards the root and applying this heapify over and over again, but I have to work backwards, okay? So starting from the middle of the array, work your way to the root, work your way to the beginning of the array, and heapify as you go. So the 4 was the first non-leaf node. It's fine as a heap, so I can leave it alone. So what I know is that this whole thing, that's a heap, that's a heap, that's a heap, that's a heap. So the next non-leaf node I look at is the 6. Okay. Now, if I take a look at the 6 and I think about this, remember we're doing min heaps here. Is this a heap? And the answer is that's not a heap. So I take the 6 and I compare it against the 5, and it is bigger. So I know I have definitely got to move the 6. I don't know if it's going to be with the 5 or the 2 yet. I then say, okay, compare 5 and 2. Okay. And since 2 is the smaller value, I'm going to trade the 6 and the 2. So the 2 and the 6 trade places. And in my array, this is just a swap, okay? 2 and 6. Okay, it's just a swap. Now this thing is now a heap. This value is now a heap. I don't have to worry about it anymore. So at this point, I am now here in my tree. I'm starting to look at this tree now. So is this thing a heap or not? And the answer is, well, I compare the 3 against the 4. And 3 is smaller than 4, so we're okay. Now we have to compare the 3 against the 1. Is the 3 smaller than a 1? Nope. So what do? We do a swap. So the 3 and the 1 swap places. And so now I end up with 1 and 3, like so. And that's basically it, because at this point, the 3 is now at the leaf node, so we have no other heaps underneath it. We're done. Okay, so that one's okay. So now what we have is we actually have 2 different heaps here. Okay, we have a heap over here and a heap also over here. So there are actually sort of 2 separate heaps at this point. And we are down to our very last node, which is 8. Now this one is going to take a little bit more time to do, but same algorithm. So we take a look at we take a look at this. Remember that the 2 children are already heaps. Compare 8 against 1. 1 is smaller than 8, so I know I have to do a swap. 1 is also smaller than 2, so I know I have to swap between 8 and 1. So 1 and 8 get swapped. 1 goes up here, 8 goes down here. Now, the moment that I do when I do heapify, once I do a swap, I actually have to heapify this, because I don't actually know that this whole thing is now a heap because I broke it, right? Because I swapped something bigger into it. So there's a possibility that I actually have to do another run, another round, right? So that's what I do next. I take the 8 and I compare it against 4. 8 is bigger than 4, so I know I have to do at least that swap. But let's check the right-hand side, which is 3. So compare 4 and 3. 3 is the smaller one, so I'm going to swap 8 and 3. 8 and a smaller child. So right here, so I've done this swap, 1 and 8. Okay, and now I have to swap 3 and 8. So 3 and 8. So over here, 3 and 8. And now 8 is at a leaf node. And we know that leaf nodes, we don't have to touch them because they're leaves. So we're done. So what we've done is we've created a heap within the array um, without actually using a separate data structure. We just simply use the array itself and say, turn this into a heap. So this is Makeheap. And what we do is we apply these heapify algorithm over and over again. Okay. Now this is the algorithm that Lab 7 talks about. So when the speaker was talking about how to like do a Makeheap, this is the algorithm he's talking about. He's actually saying, okay, we're going to just do heapify on this thing, and we turned it into a heap. in place. We don't actually build a separate data structure. We simply take all the elements and we apply heapify. Now notice that even within the partition, you don't actually apply to the whole partition. You only apply to half of it because the rest were leaves, right? So you apply this Makeheap algorithm a few times and you turn it into a heap, okay? Now, that's basically Makeheap, okay? So in the next video, so this algorithm, so instead of, if I had like n numbers to put into a heap for heap, right? Um, I don't have, and those numbers were already put into an array to begin with. I don't have to insert all n of them into a heap manually. I only have to perform make heap on the entire array, and that array turns into a heap itself. Now, this turns out to be this algorithm, make heap. Now, we're not going to prove this, but this algorithm is on. Okay, it's not actually like n log n, which is what it would be if you had to do n insertions into a log n array. Make heap itself is actually faster, and so this is a really nice idea, because if I don't have all of these operations, this is actually faster for me to do than to actually do like n insertions into a heap. So that's really neat. Um, and so we're going to actually use this idea for our sorting. Okay, so in the next video, we're going to talk about sorting, a sort called heap sort, which was actually sort of the reason we talked about heaps is actually to talk about our last sorting algorithm called heap sort. And in heap sort, what we do is we actually sort by creating heaps. Now, this is not the same thing as what Lab 7 is about. Lab 7 is about just doing the make heap part to make quicksort work faster. Because if you make heap, now notice that after I've made this heap, take a look at this array. Okay, this is a fairly small array. Doing make heap on this array required a couple of swaps, but you will also notice that when I did this, um, it, it it's kind of a little bit, I wouldn't say it's sorted, but it's sorted-ish, right? You know that the first number is definitely the smallest, okay? So that's really useful, okay? Now, so remember when he says you start your loop, you don't have to start your loop at the beginning. This is why, because you already know that the smallest number is actually at the root. You also know that the second smallest number is either here or here, for sure. You don't know where the third smallest one is, but you know where the second smallest one is. So what it actually tells you is that we already know that the first two numbers are actually they might not necessarily be in the right place, but if this is not the second smallest, it's definitely the third. Like it will be the third smallest, okay? Because actually no, you can't say that. You know that it is that these well, you know that this is increasing in order. You know that uh, one of these two numbers is definitely the second smallest. You don't know where the third one is. The third one could be here or possibly here. Like those, that's where the third smallest could be. Like this could be where the fourth smallest one is. So, but you can start by inserting this third number into the array. You don't have to start with this one being the number you put in first. This is the one you can put in first because the other two are already sort of in sorted order. You don't have to worry about it. When he talks about unguarded insertion sort, there's a guard to the insertion sort that prevents you from going to the beginning of the array. You kind of don't need it because you will never go past the beginning because you know this number is definitely the smallest, right? So the check for whether or not you are at the beginning of the array, you don't actually need that because you should never have a situation where this number isn't the smallest. So something to keep in mind when you're doing your lab 7. So when he talks about unguarded, that's sort of what it is. Okay. Now, in any case, let's talk about how to actually do a heap sort in the next video.